Thank you. Thanks. Hey, everyone. Just a little bit on my background. I was at Apple through iOS 5 and worked on a lot of the smaller utility apps like Calculator and Stocks and adding public transit to the Maps app, this kind of thing. And quite a bit on UI Kit from API review and optimization, making the keyboard faster, that kind of stuff. Went to a startup company after that called Nest Computing, and then moved on to Facebook to build Facebook Paper. And just about 6 or 9 months ago, I moved to Instagram and have been working with a really awesome team there. So today I wanted to tell you about how you can make your apps responsive with very little effort using AsyncDisplayKit. And there are a couple different parts to this. The first one is what we even mean by responsiveness. It's kind of a loaded term that's used in a bunch of different contexts. The next is a little bit about the architecture of iOS and sort of the design principles of AsyncDisplayKit. And the last is how you can actually use it and convert code and what some of the pitfalls are. So responsiveness. I've defined this in kind of 3 parts. The first one it relates to gestures and sort of dropped frames. Everyone here is familiar with this. But the idea is that regardless of the stage that your application is at, it should be responsive to users' input. So even if it's loading something, even if the user just performed an action, it should still be responsive to whatever is on screen. The next is to minimize long delays. This actually has a lot to do with network access and data loading and caching. When you actually request content ahead of time, there are a bunch of systems that are needed to do this really well. And the last, which is kind of an aspect of the first, but something that's really important to call out, is the sense of ambiguity that users feel when there is a delay in the UI. So you can all relate to when you tap a button and it does nothing, you think, you know, maybe the screen didn't sense my finger, or maybe the app had an issue. Maybe I should tap again. Maybe you do tap it again. But even if you don't have enough of a lag for the user to successfully tap a second time, there's this psychological phenomenon of almost a concern or this ambiguity of what's going on. And it's actually a very short window that can cause that thought to pop into people's minds, and it's pretty uncomfortable. So let's look at some of the history here. The web has studied this topic very extensively and has proven that even very small changes like 100 millisecond time to interact increases in Amazon, reducing sales by 1%, the end of funnel operations of just their front page load. People abandoning sites with just 3-second load times. Just small like data size decreases, massively increasing traffic. This was well recognized as critical in the web era. But nowadays it's even more important because there isn't this abstraction of the mouse to between the user's interaction and the screen. It's very direct, and the expectations are very high because Apple and other major publishers spend a lot of time working on this stuff. So users that spend a lot of their time on the platform with those apps have specific expectations that are built up from what they do. So surveys specifically on mobile, most people expect load times under 2 seconds for an app to launch. This is pretty quick. And about 80% will abandon an app and may never revisit it if it crashes or freezes just twice. So this is a pretty high bar. Now, these are some examples of like iOS 7 style UIs that have been coming out recently that have been becoming more popular. Continuous gestures, physics-based animations are everywhere. The reason I show this is because the standard of responsiveness from a technical perspective that you need to achieve to make this smooth is much greater even than it was on mobile a few years ago. And one reason for this is that stutters, even single frame drops in these kind of interactions are very noticeable to the user. So there's this very tight sensitivity to flaws. Here's an example of that. Mouse clicks, you might even be able to tolerate a 500 millisecond lag. Taps, I really think 50 milliseconds should be the high end, but maybe up to 100 milliseconds. Between 50 and 100 milliseconds, you do start to get this thought of, did it work? You don't have enough time to tap a second time, but there is some ambiguity there. But with continuous gestures, if your app hiccups for more than about 10 milliseconds, this is immediately noticeable. So one thing that's really interesting about this connection is that there is this cycle between user actions and their actions being blocked by fulfilling the request that their last action represented. So a user scrolls or taps, and this causes a new table cells to load or new view controllers to be allocated, and that actual action prevents the user in many cases from doing something else, at least doing so responsively. So what we really want to do is get rid of this sort of like back channel or impact on what we want to enable continuously is just a flow of user actions preparing content. So just wrapping this up, the two types of impacts here are like blocked interactions, frame drops, sort of gestures, but also waiting, just looking at loading spinners. And there are separate things that we can do as engineers to minimize both of these. So one important concept here, I'm sure everyone has heard about this in some capacity, is the main thread. The iOS SDK was designed at a time when the concept of mobile SDKs was very new, and so it was massively important to make the SDK as simple as possible. And threading is sort of strictly, multi-threaded code is strictly more complex than single-threaded code. And perhaps most importantly, one of the reasons this design decision was made is that multi-core phones were many years into the future, not even on the roadmap at the time that this was designed. So the reality here is that almost everything that iOS does is bottlenecked on this single thread of execution. So what are the common things that block this thread for periods that are long enough to cause issues? It turns out that most of these are related to preparing content to fulfilling user requests. The first is text measurement, which needs to be done in a hierarchical way where as you compute values at one level of the hierarchy, the results of those computations are required for the next level. So this has some subtlety to it. Rendering is a broad topic that includes a rasterization of text, decoding images, PNGs, and JPEGs, but also arbitrary graphics like shadows and shapes. Note that text in both layout and rendering needs to support many different world languages. So if you consider what it takes to rasterize Thai or Chinese or Korean, it's literally an order of magnitude more complex than Latin character sets, so you have to keep this in mind. And finally, system objects are often under-recognized. Any profiling trace will show this to you, but even just creating UI views, let alone assembling them together or doing anything with view controllers, takes a material amount of time that really adds up, especially in larger apps. So let's go through AsyncDisplayKit, first starting with how it's designed, some of its core implementation details, then getting into some of its feature set, basically the things that the abstraction has allowed to be done conveniently, and lastly into app integration topics. So in order to understand the core, it's useful to know what the design goals were. First is a generalized way to avoid main thread stalls, to move all of those things mentioned previously off the main thread by default whenever possible. And the next is to have an immediate familiarity to UIKit developers. So we didn't want to just create this alternate ecosystem. Of course, one of the most important constraints is that UIKit and core animation are not thread safe at all. You can't even allocate these objects on background threads. And yet we must integrate with them. They provide an incredible diversity of functionality that is really, really important and could never be rebuilt by any team in less than 10 years. So you're probably familiar with this, but this is basically the setup of UIKit and core animation. Here we have a UI view that creates and owns a CA layer. And it turns out that UI view doesn't even have an on-screen presence except through its layer. And so sometimes you can have layers by themselves as well. But the reason this is set up this way is because UIKit adds various features that core animation doesn't need to be concerned with, like touch handling. So this whole construct is only designed for use on the main thread, and this is part of our problem. So how could we address this fundamentally, ideally taking inspiration from how this is designed? Well, the way that we came up with is to simply extend this chain. And in the same way that UIKit extends core animation, we would like to add features to UIKit, and so we can follow that same pattern. And we've called this thing ASDisplayNode, node being a hierarchical type of concept that is distinct from a view and layer, but is very much related. And you might be surprised at the optimizations this has afforded us. So what's the mental model for this object? It's an NS object. It's not a subclass of UI view or CA layer, and instead it creates and owns one of those type of objects. And it's thread safe, so you can create them on background threads, you can assemble hierarchies of them, and it does most of its operation in the background. This is a view in the MVC paradigm. It's really important to remember that. Note that CA layer is not called a view, but it's also a view in the MVC paradigm. And so don't let the name node fool you. It's really meant to act like a view. It's a one-for-one replacement for UI views and CA layers. So where you adopt this, which may only be in certain subsections of your app, it will usually just replace those objects. They are asynchronous by default. So there's a mode where you can enable synchronous rendering, but the assumption is that you'd like to minimize interruption to the user, and so asynchronous operation is preferred. Because of this, there's also now a concept of a synchronous placeholder state. In other words, if your systems in place to render ahead of time have not been able to do so quickly enough, there needs to be some well-defined appearance that can be shown synchronously. We'll talk more about this later. And lastly, although you should prefer interacting with the Node API, you can pull out the view and layer at any time if you need to. So this part of the API, which is just a subset, is just an example of the UI view and CA layer functionality that's exposed through the node. This is to say that the Node API was designed as a superset of UI view and CA layer. This is really useful because all of these properties or methods you've seen before, you can implement a touchAsBegan method. It will be called as you've experienced in the past. You can set anchor point or content mode, which are actually layer and view properties right side by side. So in the case that there are naming conflicts between views and layers, for example, masks to bounds versus clips to bounds, we simply use the UI view name. But this actually makes the APIs of views and layers more consistent and more elegant by making them accessible in a single object. So what's actually new, that being merged old stuff? We've added a view property. So there's the layer property, as you saw before, that UI view also has. There's now add subnode, there's remove subnode as well, just like add subview and add sublayer. And some of the more interesting stuff is this method called measure, which performs an asynchronous layout pass. We'll get into this in a moment. And there's a special header file that discusses methods that are specific to subclassing ASDisplayNode. So one of those is calculate size that fits, which is called during the asynchronous layout pass. Another is didLoad, which is called when the view or layer object associated with a node is created. And another example is layout, which is called in exactly the same cases that layout subviews and layout sublayers is. Excuse me. So let's look at the life cycle of these objects. When you allocate them, there are no what we call backing objects, views or layers, because it's expected that you're creating these in the background. And it's not possible to allocate views and layers in the background. That does not mean that you have any restrictions on setting view and layer properties, however. At some point, you hand over control of these objects to the main thread, and you might want to add them to a table cell or a UI window. Accessing the view or layer property, which should always be done on the main thread, just as accessing any view or layer should be, triggers the creation of these backing objects, and it sort of fills out the tree. So after that point, when they're in a UI window, we get a call from core animation for layout sublayers. This is really simple to handle because we just perform layout and kind of complete that pass. The next thing that happens is we get a call for display from core animation. This is a little bit more interesting. We'll also go into we sort of asynchronously prepare the contents and then set it back. So let's look at this in more detail. Say that we're trying to implement this screen and focus in particular on this author label, the title label, and the body text. So we have a background queue here, and we run this line that simply allocates an object called FBStoryNode, which is the overall story. What this does is simply goes through, just like creating a view hierarchy, sets up this hierarchy of nodes, calls add subnode along the way. And then while on the background queue, we call this method called measure, which proceeds through the hierarchy and calls calculate size that fits on everything. This will simply set the calculated size property on all of these methods, and because it passes down a constraint that's calculated along the way, this actually can implement any manner of layout complexities to justification or fitting labels in different spaces. So at this point, we actually have a completely laid out, fully calculated hierarchy of objects without ever touching the main thread. So at this point, we'd like to show it to the user. So we could add it to the window. One way to refer to this is mounting. Going back here, you can use this method add subnode even on UI view or UI window objects. This is exactly equivalent to add subview with accessing the view property of a node. And so at this point, you'll recognize we're accessing the view property. So what that does is fills out the sort of backing objects of the node hierarchy. And at this point, we look at rendering. This is a little bit more complex, but you can see we are in the implementation of the layer that AsyncDisplayKit uses. We get a call from core animation to display. This is done on the main thread. So immediately, instead of spending any time on the main thread, we actually just schedule these operations on a background queue. We create the context. This is fairly costly to do. It's a big memory allocation. Then we call draw method that might render text or decode images or anything. And so this is done concurrently with multiple nodes sort of rendering together. And whenever they finish, sort of as they finish, they set their contents as soon as they're ready. And as that happens, their parents know that their sort of subtree is done. And so they may lift their placeholder states according to behavior that you've set. And once the whole tree is done, the story can be shown. So that's just sort of the underlying fundamental stuff. Don't often need to work with rendering code like that, but let's get into some of the features that make this abstraction special. A lot of them are optimizations that you sort of get for free, but are really cool. We'll go into text node and image node, which are much more powerful replacements for UI label and UI image view. ASTableView and ASCollection view are basically asynchronous versions of those classes. Talk about intelligent loading, which can help you manage your network requests automatically, and also those placeholder states I mentioned. So concurrency is one of the optimizations that we've achieved with this paradigm. Asynchronous operations are necessary to have this sort of UI smoothness we've been talking about, but it turns out that if you make use of these multi-core processors, you can also reduce the amount of time to complete showing the user interface, because the main thread, although you want it to be free for user interaction, is still only a single thread of execution. So if you're doing all of your rendering there, it's going to take longer than it actually has to. 90% of iOS devices are multi-core today, and the iPad Air 2 is actually a triple-core device, and this will keep growing over time. With AsyncDisplayKit, we use all of these cores automatically, whether it's a single-core device or a many-core device. So importantly, layout is concurrent, and so are all forms of rendering. What's really nice about this is it also improves power efficiency. It turns out that using a single core for a longer period of time is more wasteful than using multiple cores for a shorter period of time. So it's a small help, but it's very measurable. So here's another optimization. You might think that this looks like there's kind of a middleman here, like do we really need UI view in all parts of the hierarchy? It turns out that for many parts of the hierarchy, for example, if you imagine these are buttons and the label inside of them is a view, that label inside does not need touch handling. It does not need to know when it is tapped because the button itself is already handling that. So we could get rid of the overhead of UI view, and it turns out that UI views are at least 5 times more expensive than their associated layers. There are a ton of costs to views. And so what we've added is a simple Boolean property that you can set to yes, and without changing any other code, no classes, no property sets, nothing. The only major change here is that you won't get the touch callback methods if you've implemented them on the node, which if you use this in the right places will be of no consequence. So this can be a really major optimization in reducing the system object overhead that I mentioned. Another is subtree rasterization. There are a bunch of pitfalls to using rasterize options on CA layer, but this is a much safer way to compress down a tree of multiple layers that you'd like to have separate so that your layout code has an easier time moving them around depending on the circumstances. But we can set up our rendering pipeline so that we can just compress these down and have a single texture. And what's great about this is that it's both a CPU and a GPU optimization. So we avoid creating layers and views for all of those things, but we also avoid blending on the GPU on each frame. So let's look at some of the components that you can directly use. ASTextNode is based on TextKit and has a bunch of really cool features like flowing subnodes inline so that you can have asynchronously rendered images that your text actually wraps around and still support asynchronous layout and asynchronous rendering. And another cool feature is very easily there's a customizable way that you can show placeholders that using the information calculated during asynchronous layout, we can show these sort of lines where the text will actually show up. And so it's of a minimal sort of visual prominence when the content comes in. Of course, this is a slowed down example. In most cases, the render ahead should succeed at rendering the text before it's on screen. ASImageNode is also an asynchronous image view replacement. This supports multiple image qualities. So you can give it a list of URLs, for example, and depending on what you have cached locally, what your caching strategy is that you set on it, it can automatically and asynchronously sort of advance through the qualities as quickly as possible. So this will also an exaggerated low quality example, but you can get much higher user engagement by showing something very quickly, gives the user a sense that the network is working and that if they wait longer, a better version will come in. And it's likely we'll add progressive JPEG support to this, but right now it's for separate image files. ASTableView and ASCollection are really important, really interesting classes. These do a ton of work for you, and they have full editing support, animation support. They are actual subclasses of UITableView and UICollectionView, and this makes sure that the behavior matches exactly, so that we're not chasing any sort of small variances in calls. It automatically manages concurrent layout of cells ahead of time, as well as concurrent rendering, and has configurable windows for network requests ahead of time, as well as rendering requests, and these are separate ranges that you can manage. So let's look at that, which one way to refer to it would be intelligent preloading. This is a horizontal example, but please also imagine this for vertical table views. We have the visible range here, and we define something outside of that called the render range. This is small on the side that the user is moving away from, but in case they scroll back a little bit, we want to keep some content there. And it's large on the side that they're moving towards so that we can prepare this content asynchronously in advance. And there's also a network range, and this allows entire node hierarchies like these stories to get calls to let them know that they should start loading their content. And so this helps the multiple representation image view, for example, prepare in advance. So what's cool is that in addition to being able to adjust the leading and trailing edge of this, it will automatically flip around if the user goes in the other direction and start trying to catch up to what the user is doing. And so the reason that this is asymmetric, although you can set it to whatever value you like, is that it saves memory on the trailing side and allows you to spend more on the preceding side. There's a simple property range tuning parameters that can change that, and you can adjust this for different device types depending on your RAM limitations or how much CPU they have. And so placeholders, this is what happens in a really slow phone if you're scrolling really fast and you don't finish sort of preloading in time. These are customizable using background color, which is free of cost to use. It's rendered by the GPU. You can set a placeholder image, should be pretty quick to decode because this is synchronous. You can even set the placeholder to fade out nicely when the final content is done. And you can change the appearance of the text placeholders as well. If you'd like more options, we're thinking about further improving this API. So let's wrap up looking at app integration concerns. There are a number of different aspects to this. The first is like a mental model of where you should use nodes. You shouldn't convert absolutely everything in your app. And we'll get into some code conversion examples so you can see what's required. Subclassing, wrapping, just very briefly, wrapping being existing UI kit components. How this works with Autolayout and Interface Builder. Nodes don't need to replace every view. What's the best place to convert usually is the table view or collection view. This is why the ASTableView and ASCollection classes are actually views. They're not nodes, because it's sort of a reminder that you can replace your UI table view reference with an ASTableView, and that will ask you node for index path instead of cell for index path. That does a lot of this work automatically for you in deciding when to render ahead, managing memory, and this kind of stuff. Other things you might consider are view controllers, where when you tap, there's a big delay, launch path stuff to make your app responsive faster, or especially in apps that have a lot of continuous gestures, you might want to use it in a broader group. But mainly, the table view and collection view will give you the majority of the advantages. So let's look at converting this view. We have a UI label here, and let's start by converting that to a text node. So as we proceed, we change one reference above and another reference down. 2 lines change, sort of an autocomplete based operation. The frame property is the same. Sorry, there is a 3rd line here, which is the add subnode call instead of add subview. Alternatively, you could add a .view and continue calling add subview and just make it label.view. So with that done, let's look at converting the containing class to a node as well, perhaps to support asynchronous layout. So we derive from a different class and we change the layout method, but nothing else actually needs to change. So layout is still called at the same time, but it's just called layout instead of layout subviews to be a more general name. And if you derive from ASDisplayNode, since it has all of the same properties as UI view plus a few extra, most code will just work. So subclassing, if we were to build this out a little bit more, if we wanted to support asynchronous layout, for example, we would implement something like this calculate size that fits method that calls measure on subnodes to ensure they all have a chance to lay out in advance. We don't need did load here, but it's a great time to allocate a gesture recognizer and add it to the view, because gesture recognizers are also main thread only, and they're never needed before the view is allocated, so it's a perfect time to do that. How about these collection views or table views? This is cool because they are still views, so the conversion is really very straightforward. The first 2 lines changed here actually have 2 characters replaced, and the third is just a method name. So we have ASCollection View instead of UI Collection View in 2 places, and then instead of cell for item, we have node for item. This supports the same UI Collection View flow layout objects, literally the UI version, so there's no special AsyncDisplayKit version of that. Lastly, getting into wrapping existing components, ASCollection is one example that we provide that's basically like a scroll view. If you wanted to do this manually, it's very easy. You'd simply write init with view block and provide a block that performs the initialization of any view. This will result in a node that has the isSynchronous property set, but that only applies to that node. It does not apply to any of its children. And in the case of a scroll view, it doesn't have any content of its own to render, so this is inconsequential. It does participate in asynchronous layout, though. So what about layout and auto-resizing, auto-layout type features? This is supported. It works fine just like all UI view features, but because it's controlled very tightly within UIKit and there is no way to prompt auto layout to occur on a specific thread, it is synchronous. So this will play just fine with existing code that uses auto layout, but you won't get the advantage there. Fortunately, the asynchronous rendering is still supported and doesn't have any particular gotchas. And asynchronous rendering is actually more impactful and more important than asynchronous layout. We're thinking about adding the box model layout from React Native that was recently announced. A lot of people think this is better than the constraints-based approach anyway, but we'd love to hear if you'd be interested in that, and we'd be able to support asynchronous layout with that kind of approach. Interface Builder is not supported. It's also not supported by React Native. It's also not supported by Reactive Cocoa or by components, which is how the main Facebook app is built. It's not really supported by anything that's not very standard. And it turns out that the most commonly described example of what storyboards are is incompatible with truth and beauty, so I do recommend that you train off of it. So what are some of the technical takeaways here? The first is that there's a lot of work required to build a responsive app. Unfortunately, AsyncDisplayKit cannot do all of this for you, and in fact, in this list, there's one thing that it can't help you with at all. But the other things it can help you with at least a little bit, sometimes very significantly. And so take a look at it, see if you can delete some code and have fewer bugs. After designing this, I had a realization that there was a pretty significant variance from one of the most established software design principles that I've often heard, which is you should divide and conquer. That approach would mean that you should solve slow text rendering in one way, you should solve slow image decoding in another way, maybe address layout in a different way than rendering. But it turns out that unifying a problem set and abstracting can be extremely powerful and not only be easier in many cases, but actually more successful and achieve things that you didn't really expect to be able to do, like some of these optimizations around subtree precompositing that sort of came for free with this. Another is to accept the challenge of ambitious designs. It's very tempting to tell a designer, this is impossible, or this is just really hard, or kind of feel bummed out about how much time it's going to take. But sometimes if you look around at different approaches that you haven't tried before, it can be easier than you expect. And what's really, really important about this is that once you learn those techniques, then you are free to use them for future designs, and you can really sort of like raise the bar of your app and your team overall. So next time, even if something seems really ridiculous, spend a few minutes thinking through if it might be possible. You don't have to tell the designer you might be thinking it could be done, but give it a thought internally. And lastly, don't reinvent the wheel. We all kind of know this, but you might think something like this should be based on OpenGL, but we'd lose UI WebView and UI text field and UI gesture recognizer and so many other things, and it'd be less familiar to people. And so, really use existing components where you can. And I'd also like to announce today that we're launching AsyncDisplayKit 1.2, which has a bunch of cool updates. We have ASDisplayNode, which is basically an animation-friendly version of text field that, even as a user is typing, we can dynamically animate the text size in a way that doesn't interrupt their typing speed. We have these network range APIs that I mentioned so that content, you'll get callbacks for your own subclasses, or the default classes will automatically request image assets and so forth ahead of time. And also batch request APIs. So if you have groups of stories or something that you request from the server, there's a configurable distance ahead of reaching the end of content that you can set to sort of drive your network code. Go to asyncdisplaykit.org. You'll see a link to the GitHub there. And perhaps most importantly of all of this, we've been thriving off of the feedback from the community. We've been adding features like crazy based on exactly what the requests are that we've been getting. And so that's super valuable to us. And I ask that if you're interested, join fb.me/asdk-dev. This is a Google group we're getting started. Links to our Facebook group that has a bunch of traffic in it from the past as well. You can ask us any implementation question about your app, even if it doesn't use AsyncDisplayKit. But we can also help with technical problems on ASDK. Share your experiences using it. Suggest improvements, send us pull requests. We've been pulling in a lot of code changes from the community as well, which has been awesome to see. And lastly, I think we have about 15 minutes for Q&A. So thanks.
I love the part when you said that the good coding may reduce the carbon footprint. This is the most interesting part. As for me, I'm not a coder, so
yeah.
I need to ask a question. I would never have a better possibility to say that. Some of the things that you said, the general goals, it looks like they are already implemented in native, the main Facebook client, but definitely not in Pages Manager. Could you just say a few words, the differences between design and principles between those two, most downloaded apps from Facebook?
Sure, yeah. The main Facebook app also has a different engineering approach. It's been discussed recently. There are a few blog posts on it. It's called Components, and it's been a long time in the making. It's a really powerful framework that has a very different design than AsyncDisplayKit, but has some similar capabilities. The biggest difference is that it's declarative. So it's a much bigger departure from UIKit patterns, and it does have some complexities around interactive interfaces, responding to gestures, animation, this kind of thing. But it is incredibly successful in building certain kinds of apps, including the largest app in the world. And so that that approach has been filtering out to different apps. So I'm not sure if Pages Manager is using components yet, but it certainly could. And yeah, I think as far as design, Facebook is definitely a leading center of design talent. The challenge to sort of shipping new designs is ensuring that it does what users want and what users expect. And so one thing with Pages Manager is that it's relied upon as an important utility for businesses around the world, and you can't just change the interface arbitrarily. So there is a process to rolling out design improvements.
So business people could wait more than half a second for interface to load.
I definitely would not say that at all. But the process just making changes and sort of verifying those changes does take longer. Not that the bar for quality should be any less by any means.
Okay.
Thanks. I have a question related with Autolayout and rotation. As I see in the paper app, it's usually a problem when you have opened, for example, article, it doesn't rotate. So my question is there something specific we should think about when using AsyncDisplayKit together with Autolayout and also taking rotation into account?
Sure. So if you were to use Autolayout for everything, everything would be synchronous. So in other words, like the text layout and stuff would be on the main thread. If you do that, then there shouldn't be any concerns with rotation either. The main reason paper doesn't rotate is it's an additional design complexity that we didn't have time for. It's not a technical limitation. The article's sort of open in this booklet, and if you were to rotate the content, then how that booklet sort of closes is not obviously defined and would be complex even from like a user understanding perspective. What you would want to consider for rotation, even if you did use Autolayout, is that sometimes you need to redisplay components like actually re-render them. So there are methods to do this to say if you resize a node, it's going to want to re-render. You may have to clear its contents, just set the contents property to nil, and that will restore its placeholder state. So there might be a couple calls you have to add to handle that correctly, but there are recursive methods of this that will do it for a large hierarchy in 1 or 2 lines. So join the group and be happy to work through that.
I had a question here. With the text placeholder nodes, you still have to lay out the text even though you're not rendering. Can you say something about the trade-off there? Like if you're bothering to lay it out, why don't just render it?
So there is that's a good question. There's a big difference in the amount of computation required for layout and rendering. It's about an order of magnitude for like Latin text, for example. Some languages are closer, but unilaterally more expensive. Others are actually much simpler to lay out than they are to render. The reason is that because they aren't equivalent, because rasterizing the fine level details of anti-aliased curves of glyphs is a very, very intensive vector to raster conversion, allocating large buffers of memory, this kind of thing, as opposed to calculating the spacing of words and where the wrapping rules, this kind of thing. So there is a big difference there. The reason that placeholders are not that expensive is that Cortex, in doing this operation, already calculates the exact bounds of each line separately. It's just that normally, if you're interested in sizing a block of text, you just want to know its outer bounding box. The reality is that in order to come to that answer, it must determine the size of each line along the way. And so we essentially have that information for free, especially because it's prepared asynchronously.
Okay, thank you very much. Oh, sorry.
I know it's a bit tangential to your slides, but do you use Metal or OpenGL in any of your kit or your applications in Facebook?
Yeah, it's a good question. Some design tools use it, but not in shipping code. AsyncDisplayKit very seriously considered using OpenGL, but for the reason I mentioned, a few reasons about API familiarity, but also integration with existing components, it really wasn't a good or feasible option. One of the cool things, though, is that when I added the layer backing feature, it was a good opportunity to sort of clean up the abstraction so that nodes are no longer dependent on just UIKit because they can actually operate with just core animation. And so that's been abstracted in a way that would make it very technically feasible to enable like an OpenGL backed mode where the same sort of client code could actually drive layers. You could imagine even providing fragment shaders for a subtree of your user interface. Now, there would be a lot of caveats with this. Like, we would have to either not support or re-implement event handling. It would not coexist with layers and views in the same way that it does now. So it'd be a much more all-in sort of option. But from a technical level, it could be supported and it would have some interesting capabilities, but we haven't pursued it yet.
Hi. I want to know, like, basically you guys just made UIKit asynchronous, like something that Apple should have done. Like, what Apple, did Apple say something about it? Like, do you know about the engineers from Apple, what they think about it? They're going to also implement something like that, or?
Yep, I've talked a lot to Apple about this and friends there. Apple optimizes a lot for the simplicity of the API. And so, interestingly, something a couple friends pointed out to me is the existence of this framework proves that Apple does not need to address this problem, because the developers that care about this sort of higher level of responsiveness can actually achieve it with their frameworks. Honestly, that is a pretty good answer, because the reality is that on Android, as an example, there are not just one or two things that make this same design not work, but at least 4 or 5 huge roadblocks. Like, for example, text rendering can't be done in the background at all, and certainly on earlier versions, you can't create a space in memory, draw into it, and then assign it to an existing view. These are things that work really nicely with Apple's frameworks, and it's credit to their implementation that it's so extensible. So they may add some things like maybe asynchronous image decoding, but from what I understand, it's not going to happen that they'll support asynchronous layout or arbitrary rendering.
Hey, right here. You can. What do features like layer backing and rasterizing a node and its children, how does that interact with accessibility?
Very good question. So accessibility is fully supported in regular nodes that have a UI view associated with them. You are spot on that if you enable layer backing or subtree rasterization, you lose some fine-grained control over accessibility in that subtree specifically. Although I believe, I may be wrong on this, but I believe we extended this so if you provide your own subclasses, you can return accessibility labels and so forth. And so we walk down the node hierarchy a little bit more. There's some interplay with the accessibility system that mitigates this, but it is an important thing to think about.
Okay, we run out of time, but it's really easy to recognize code.
What's this?
It's really to recognize it because you've cheered. So just
yeah, feel free to find me. I'm really glad to have been able to come out from California to see you guys. I do have to actually catch a flight very soon after this, but we'll be around for 15, 30 minutes. Join our fb.me/ASDK-dev, and I'll answer any question you throw at us.
Thank you very much.
Thank you.